WD9XYZ, and I don't like that call sign. The X is terrible for phonetics. I like the W9BOO for Halloween. And they'll say, if it's available, okay. And that's the way it works. You fill out a form, you can actually put a list of them. You know, if you can't get this one, then this one, then this one, then this one. But most people just put one because they look it up and they say nobody's got it. So chances are it's not going to disappear the next month. And voila, you got a new call sign. Your old one becomes, in the FCC's database, as your former call sign. It'll still be there.
You can also look it up on QRZ.com, see
Yeah.
what's available, and then choose which one you please. So that you guys know.
QRZ.com, oops, is a very important website to get to know. It's how you look up people you contact, like where they live, what's their real name, etc. It's got the call sign database. You can also go to the FCC's website and do it. The only difference is with QRZ, if you want to look up a call sign, you have to become a member of QRZ. But it's free. You just give them, you know, your little bit of personal data, like your email address. Pick a login and a password, and you're there. You don't have to spend anything to do it. They just want to know who they're dealing with. Well, once you're there, you can look up call signs, and you can look at your call signs, see how many lookups there have been. Get an idea of how popular you are, or how notorious, or how really valuable your call sign is. Barry Katz-Nelson is a guy in our club with W9NDU. Used to belong to another club member, Harry Markowitz, who passed away of cancer many years ago. And Barry and Harry were good friends, so Barry adopted Harry's call sign. Harry thought NDU stood for numb, dumb, and useless. At least that's what his wife called it. Harry's a really nice guy, though. A lot of people call Barry saying, I'll pay you if you'll give that call sign up and let me have it. Because I graduated from Notre Dame, and NDU looks like Notre Dame University. People, you know, it's just like internet domain names. People will put some real money on the table if you've got a letter combination that they want for whatever reason. Okay, what I want to talk about next is antennas. What, pray tell, makes an antenna? That is what an antenna really is. Piece of wire. Two pieces of wire. One going this way, one going that way. It's not so much that they are anything special other than the fact that they're cut to a certain length, stretched out, conduct electricity, and in all other respects, no other way, shape, or form really become remarkable, except for things you do with them to make them do funny stuff. An antenna really comes down to just that. It's got two poles. It's got, think about the fact that it's energized from a circuit like this. Current is going to flow this way, and then it's going to flow, and if it flows this way into this element, it's flowing that way, current. And it oscillates, it goes back and forth. So current is going like this, and it's going like that. But when it gets to the antenna, it's doing something a little different. Let me draw this picture with a darker color so that our friend Chinny, who's been reading my tapes. By the way, do you know about that? If you go to NS9RC CAM class, not on the internet, but on YouTube, youtube.com, go there and then put in this search key, you will find, as they will tell you, since you put them there, all the classes that have been taught, the one by Greg Lave in the first session on the 1st of October, the ones I've done since. And there is your chance, if you didn't get to all my classes, to see the one you missed, or if you think this stuff is too complicated, you want to read it again after you've had a couple of beers, do it at your leisure. There's a really cute picture of this girl, you know, leaning back in the chair, you know, operating the equipment, and you keep thinking, What's your name? I want to come over and visit you. It looks great. That's how you find me. And so I gotta make, and one of our people that's interested in taking the test is a Salvation Army member who was in Wisconsin, can't easily make this class, so I said, just find it on the internet and watch it if you want to sit down for a couple of hours, entertain yourself. You can get what everybody else here is getting. It's just that maybe my beautiful pictures aren't as visible on the small screen, but my wise words will come through loud and clear. All right, this is what an antenna is. This is how it connects to the real world. There's usually another coil here, connected to some kind of amplification device here, whether it's a vacuum tube or transistor or whatever. And whatever, you were coupling radio frequency energy, very high frequency AC, from here to here into there. And what makes the antenna do its thing is its physical length, because what you're going to get are two kinds of waves. The antenna itself is going to have a wave that looks like this. I'm just doing a dotted line here to say, yeah, that's a normal cycle of a radio wave. Remember, radio waves may be oscillating at a very high frequency, but they move at the speed of light. So if you had a 1 million cycle per second oscillation and the speed of light is 300 million meters per second, in one oscillation at 1 million cycles per second, the thing's going to move 300 meters. So your antenna, to cover half a wavelength, notice it's not a full wavelength, it's only half, and I'll show you why. Would have to be 150 meters, and a meter is what, about 3 feet, 39.37 inches. 150 meters is still like 450 feet, that's a long antenna. So for 1 megahertz signal, you need a lot of wire. Now, we operate typically at, 14 megahertz is the 20 meter band, very popular. So you're 20 times faster than that, you're 1/20th of that, 450 feet. So you're more like, 20 some odd feet, which is more manageable. You can hang a wire that long in your backyard and not have too many problems. Why do I only need half the wavelength, I hear you ask? I shall show you. Don't take my word for it, watch. I did this before. Here's a beaded chain. What do you see here when I pull it and let it oscillate? A wave that goes up and down. This is fixed at 0, this is fixed at 0, it's not going anywhere. It's only the stuff in between that bounces up and down. And that's an oscillating system. That's actually a wavelength. So, think about it. In this cycle, you got exactly the same as you have in this half cycle. It's the same as the stuff in this half cycle. They kind of replicate each other. It's just that this guy's negative while that guy's positive and vice versa. So, you really only need, where the end of the wire is, you're going to have 0 current flow because wire can't have current flow where it isn't in existence. And this is the end of the wire, so there's no current flow there. It's in between where you have current flow. And if the wire is cut to a length such that it's half the wavelength of the radio signal you're trying to beam out, you will have this condition where the wave just, like that beaded chain goes, it will appear to go up and down. The peak will be in the middle, the endpoints will be 0, and this wave will be called a standing wave because it looks like it's standing still. And if you have a properly constructed antenna, you want a standing wave because that's how it couples energy to the atmosphere and, beams itself out to other parts of the world. What's going up and down these two wires, since they're not stretched out, is something a little different. It's going to be sort of like this. And it's going to be interestingly symmetrical. Well, this and this pig should be about the same, but I'm just trying to make a point here. What goes up this wire should look equal and opposite to what's going down the other wire. So this current and this current should be equal and opposite, and together they produce nothing, zero, zilch. This kind of thing is called a traveling wave. Aren't you happy that this is stuff you don't see in the book? If the book would be so kind as to show this stuff, it would tell you a lot more. That's why I'm here. Trying to make up for what folks on the subject don't teach. It's traveling because this thing's actually moving. This wave actually slides along that wire. Now what's different is these two wires are close to each other and they're running parallel. That part of the system is called a transmission line. Or you can call it other things. Some people call it the feed line. Some people call it the coax, because sometimes it's a coaxial cable, but not always. Some people call it whatever. It's the thing that gets you from here to there. Take a look at your TV antenna. You got this when you had a TV antenna. Anybody still have a TV antenna? Go on. Relic. Dinosaur. Yeah, when we had TV antennas back in the old days when we were kids, you had this stupid looking thing on the roof, and generally looked like this. If you were living in the city, not too far away from the transmitter, you had this loop in the middle, and you had a long element here and a short element there, and you pointed it toward downtown Chicago because that's where all the stations were, and voila, worked fine. The stuff connected to it, if you're really old enough, was two pieces of wire together in a brown jacket, and they called that stuff flatline or 300 ohm cable. Or TV antenna wire. No.
Twin lead?
Twin lead, yeah, very good, that's a good one. Call it twin lead. And there's actually a variation on that where you have sticks because sometimes they're farther apart. They call that ladder line for obvious reasons because that's what it looks like. And don't see much of that anymore either. The stuff you do see is this coax, which is coaxial cable, meaning cables where two conductors have a common axis. That's the coax part, common axis. The center is a wire, and the outer is a braid of woven metal, which we think of as the jacket or the shield. And or the braided stuff. And that's what we use all the time now. People say, well, you don't lose as much signal, that stuff works better. That's not true. This has lower losses than that. So that's not the reason we use it. The reason we use it is something rather simple, but something elegant. The outer conductor is usually tied to ground. When you tie something to a cold water pipe that's connected to the earth, you got this immense set of parallel paths in the earth, so that essentially, no matter what voltage you apply to the earth, the impedance really doesn't change. And the current doesn't really, the current will essentially be close to infinite because this thing is a very low, very low impedance. And that's what you want. You want something that's going to have what's called a fixed potential, meaning it's going to have a reference that will not change, and something that uses the earth as one of its collection points for current. In other words, if you had a voltage source here connected to earth, and it went through a load connected to earth, that's the return path. But this potential, remember, voltage is a difference potential, negative here, positive here. The potential between these 2 points, if you tie one of these to ground, is going to be consistent. And another voltage source somewhere else, tied to earth, is going to have the same potential on the negative it's tied to ground. And the importance of doing that is that fixed potential that you get means that whatever goes on inside doesn't affect that outer shell. That outer shell is going to have one solid wall of apparent potential, and that is a shield. That means what happens in Vegas, what happens in the center conductor stays inside that coax. And that's what you really want. You don't want this to leak out. These guys, if you put a pickup device near it, a loop of wire connected to some kind of listening device, you can actually receive signals from it. There's leakage. Worse, you're putting it on the side of your house. And how do you do that? You have these things, these rings that go around it and get stuck in the masonry as guides to hold it in position, right? So it comes out of the house, it goes to a ring, a few feet more, another ring, another ring, another ring. By the time it gets to the antenna on the roof, it's seen about a dozen rings or more. You've got current flowing through these wires. When you have current flowing through a wire, you got a magnetic field around it. When you have a magnetic field around it and it sees a ring, it hits the ring, it bounces back. You've got a reflection. I don't think I can demonstrate that part very well. I keep trying. It really happens, but you know, if I had a big thick piece of rope and I tied one end to the doorknob, being a boater, maybe I should use a clove hitch, right? Yeah, I know my that's okay. And I were to hold this thing here and I'd snap, it doesn't go very well. You know, basically if I snap my wrist, a wave will travel down the rope. And when it hits the end, it will bounce back. There will be another wave going actually 180 degrees out of phase. The thing will